Welcome to the Explainer. I am so thrilled to have you here today. So, we're going to be tackling an absolute beast of an interface, but don't worry, we're going to do it methodically. We are diving deep into Chrome DevTools, specifically the Performance tab. Look, if you've ever opened a performance trace and felt completely overwhelmed by that massive wall of colors and graphs, you're in the exact right place. Take a breath, get comfortable, and let's figure out how to navigate this incredibly powerful diagnostic map together.
We have all seen this IT support ticket, right? The site is slow, or the checkout is freezing. It's honestly incredibly frustrating because it's just so vague. Users are reporting symptoms based on their feelings and their isolated experiences. But as support engineers and developers, we can't fix feelings. We need objective, hard data. We have to replace opinions with facts if we're going to effectively escalate these issues to engineering. And the Chrome DevTools Performance tab is exactly how we get that data.
Okay, to make sense of all this, we're going to break our agenda down into 5 simple parts. 1, recording a performance profile. 2, decoding the flame chart. 3, spotting core web vitals. 4, isolating JavaScript bottlenecks. And 5, walking through a real-world frozen checkout scenario. Let's kick things off with part 1, recording a performance profile and setting up our equipment. Before we can analyze a single thing, we need to capture the data. And you really got to be strict with your setup here, because if your environment is messy, your data will be messy, and you'll just end up chasing ghosts. First things first, always open Chrome in incognito mode. Why? Well, because browser extensions inject their own JavaScript into pages, which creates a ton of noise in your trace. Incognito guarantees a clean slate. Second, jump into the capture settings and set your CPU to a 4x slowdown. Your powerful desktop processor is going to easily hide performance flaws that a standard mobile device will absolutely choke on. So this 4x slowdown simulates realistic mobile constraints. Then, just hit record, interact with the page exactly like a normal user would, and click stop. DevTools will crunch the numbers and build your trace.
Moving right along to part 2, decoding the flame charts and reading the map's legend.
So, you click stop, and bam, DevTools hits you with this overwhelming wall of data. Do not panic. We're going to calmly look at just one piece of this map at a time. The absolute most crucial concept here is the main thread. This is the primary battleground for web performance. Think of the main thread like a single-lane highway. It uses what's called a run-to-completion model. That means once a vehicle, or in our case a task, starts driving down the single lane, it literally cannot be interrupted. If a massive, incredibly slow-moving semi-truck of a task is on that road, user inputs like clicks, taps, or scrolling are just stuck in traffic right behind it. DevTools visualizes this as an inverted flame chart, sometimes called an icicle chart, where time flows from left to right and the call stack descends vertically, so you can see exactly which functions are calling other functions. DevTools actually uses a brilliant color coding system to help us figure this out at a glance. We really want to build some visual muscle memory here. When you look at the main track, yellow means scripting. That's your JavaScript doing its thing. Purple indicates rendering, meaning style recalculations or layout shifts. Green is painting, which is the browser actually drawing pixels onto the screen. And gray represents internal system tasks. So whenever you see a massive block of yellow, you instantly know JavaScript is hogging that single-lane highway. To put this into perspective, let's compare a fast page to a slow one. A fast page is going to have a pretty sparse, empty-looking flame chart. The browser does a little bit of work, and then it just rests, waiting for the user to do something. But a slow page, the kind users are complaining is janky or frozen, has a visually dense, deeply stacked chart. It looks like a solid block of warm colors, which means the CPU is absolutely maxed out, desperately trying to churn through complex code. And that brings us to our magic number, 50. 50 milliseconds. In the world of web performance, the 50 millisecond threshold is basically the law. If any discrete piece of work, whether that's scripting, rendering, or parsing, takes longer than 50 milliseconds to execute on the main thread, it officially crosses the line into dangerous territory. When a task breaks that 50 millisecond speed limit, it becomes what we call a long task. And DevTools literally red flags this for you. If you zoom generously into the flame chart, you'll actually spot a red triangle right in the top right corner of the task block. On top of that, the exact portion of the task that exceeds that 50 millisecond threshold is shaded with diagonal red stripes. Those red stripes are literally mapping out the exact moments where the browser is frozen and ignoring your user. All right, part 3, spotting core web vitals, finding our landmarks. Now that we know how to spot frozen tasks, let's jump up to the timings track to find some crucial user experience metrics. This track lets you trace the entire chronological journey of visual rendering. You're going to see markers for first paint, then first contentful paint, but the big kahuna we really care about is LCP, largest contentful paint. That specific marker pinpoints the exact millisecond the most significant piece of content, like a massive hero image or main headline, finally becomes visible to the user. As support engineers, you absolutely need to know what a passing grade looks like to validate these user complaints. For largest contentful paint, or LCP, we want that happening in under 2.5 seconds. For interaction to next paint, or INP, which measures how snappy the page feels when you click or tap, we need that under 200 milliseconds. And cumulative layout shift, or CLS, which measures that super annoying visual jumping, needs a score of under 0.1. If your trace is showing numbers higher than these thresholds, you've just successfully verified the user's complaint with hard data.
Which brings us to part 4, isolating JavaScript bottlenecks by focusing on the code.
We found the red flags, we checked the vital signs, and now we need to dig a little deeper. We're shifting from high-level visual metrics down to the actual underlying JavaScript that's freezing the UI. To catch the culprit, you have to understand the difference between two metrics: total time and self-time. Total time includes the entire duration of a function, plus all the other functions it calls beneath it. But self-time, that only accounts for the execution of the function's own internal logic. When we're hunting for performance bottlenecks, we're looking for functions with a high self-time, because those are the actual blocks of computational heavy lifting that are clogging up our main thread.
And finally, part 5, the frozen checkout scenario, where we actually catch the culprit.
Let's piece this all together for a real-world detective story. Imagine you get a ticket saying, "Hey, the e-commerce checkout button freezes when I click it." This is the ultimate question. The user clicked pay, and the screen just froze. We know from our in-app metric that the browser took way longer than 200 milliseconds to respond. So we fire up incognito mode, set our 4x CPU throttle, hit record, click the checkout button ourselves, and hit stop. Now we just have to hunt for the root cause. Here is your rapid-fire sequence to cut through the noise. First, scan the main track for yellow blocks with that warning red triangle and those red stripes. Boom, there's our long task right after the click event. We click on that specific task. Second, we look down at the summary tab at the bottom of the screen. It confirms a massive block of scripting time. Third, and honestly, this is the pro move right here, we click over to the bottom-up tab. The real magic of that bottom-up tab is how it completely unmasks the offender. By default, it sorts by that crucial self-time we just talked about. But if you use the drop-down menu and select Group by Product or Group by Domain, DevTools aggregates all of that execution time. Suddenly, the true offender is glaringly obvious. It's not even our core checkout code. It shows that an external marketing analytics script, or maybe a third-party chat widget, is consuming 800 milliseconds of main thread time right as the user clicks pay. We just replaced a vague checkout is broken complaint with third-party script X is causing an 800 millisecond long task on checkout. Now that is an incredibly actionable ticket for the engineering team. And just like that, you've leveled up your diagnostic skills. You now know exactly how to set up a clean trace, read the colors of the flame chart, spot the red stripes of a long task, and trace it down to the exact third-party script causing the traffic jam. So I'll leave you with this final provocative thought. If you ran a performance profile on your site's absolute most critical user flow today, right now, how many 50 millisecond red triangles do you think you'd find hiding in the trace? Go open Chrome DevTools, hit record, and start investigating. Thanks so much for joining me on this explainer.